Alright, in this video, I'm going to present a study of Euler's gamma function. This function is denoted by the Greek letter gamma, the uppercase, and it's defined by the integral from 0 to infinity of t to the power n minus 1 e to the minus t dt. So for whenever this integral is convergent, so the gamma function satisfies the following properties. So the property number 1, the gamma of 1 is equal to 1. Property number 2, the gamma of n plus 1 is equal to n times the gamma of n. So this is a recurrence relation. And then property number 3 is related to property number 2. The gamma of n plus 1 is equal to n factorial. This is for the case where n is a positive integer. So in fact, for this reason, gamma function is also known as the factorial function. As the factorial function. Then property number 4 says the gamma of 1/2 is square root pi. And then property number 5 says the gamma of p times the gamma of 1 minus p is equal to pi over sine p pi, where p is a proper fraction. So let's call this one equation number 6. We are going to prove these properties here, and then in the next video we're going to see how the gamma function can be used to evaluate integrals. So for property number 1, so it says the gamma of 1 is equal to 1. So on the left hand side we have got the gamma of 1. Now if we plug this into equation 1, it's going to be t to the power 1 minus 1 e to the minus t dt. So this is going to be integral of t to the power 0 e to the minus t dt. So this is simply integral of e to the minus t. So this is going to be the negative integral of e to the minus t from 0 to infinity. The infinity one is a limit, so it's going to be the limit as alpha goes to infinity of e to the negative alpha, and then the other one is going to be e to the 0. So that's going to be equal to 1, but we know that e to the minus alpha, as alpha goes to infinity, that one goes to 0. So that is going to be equal to 1, and that sorts out this proof. Then property number 2 says that the gamma function of n plus 1 is equal to the gamma function n times the gamma function of n. So again, if we work on the left hand side, so the left hand side is the gamma of n plus 1. So if we plug this into equation number 1, this is what it's going to look like. Then if we do integration by parts here, so if we let u be t to the power n, then du is going to be n t to the power n minus 1 dt, dv is e to the minus t dt, then v is going to be negative e to the minus t. So that means this thing is going to be equal to uv is going to be minus t to the n e to the minus t from 0 to infinity minus the integral of, but because of this negative here, this is going to be all positive, so that's going to be t to the power n minus 1, which it was supposed to be n minus 1 there, and then e to the minus t dt integral from 0 to infinity. Now again, this can be shown by L'Hopital's rule. As t goes to infinity, this term is going to go to 0 much quicker than this one. So this whole thing is going to go to 0. And then, of course, when t is 0, this thing is going to be 0. So this term is going to be 0. And then the second term, if we factor out n, is going to be integral of 0 from 0 to infinity t to the power n minus 1 e to the minus t. Now you're going to notice that already this is just the gamma function of n. So that means this thing is n times gamma of n, which is the right hand side. Okay, then property number 3, we are going to prove using mathematical induction. So gamma of n plus 1 is equal to n factorial. So in mathematical induction, we have got 3 steps. The base case, if we let n be equal to let n be equal to 1, then this thing is saying the gamma of 2 is equal to 2 factorial, which is so on the left hand side we're going to have 2, on the right hand side we're going to have 1. So gamma function of 2 is 1 factorial, which is 1. So gamma of 2 is going to be the integral from 0 to infinity of t e to the minus t dt. Again, if we use integration by parts here, so if u is t, du is going to be dt, dv is e to the minus t dt, so v is going to be minus e to the minus t. So our integral is going to be negative t e to the minus t from 0 to infinity, this is going to be plus again. It's going to be e to the minus t from 0 to infinity. Using similar arguments to what we did in the previous calculation, this is going to go to 0, and then this integral here is the same as the integral we did in property number 1, this one here, and we've already seen that that integral is equal to 1. So that means this is equal to 1, which is the same as the right hand side. Then in step number 2, we are going to assume that for some value of n, which is equal to k, then gamma of k plus 1 is k factorial. So assume this is true. Is true for some n equal to k, where k is some positive integer. Then in step number 3, we want to prove or test whether this is going to hold for the next bigger integer. So this side we want to get k plus 2, and this side we're going to have k plus 1 factorial. Now if we start working on the left hand side, gamma of k plus 2, using property number 2, is going to be equal to k plus 1 gamma of k plus 1. And then from step number 2, gamma of k plus 1 is k factorial. K factorial times k plus 1 is k plus 1 factorial. So this is now equal to the right hand side. So we can conclude that the formula is going to be true for all positive integer values of n. So that's property number 3. Property number 4, we have the gamma of 1/2 is equal to square root pi. So this one, if we plug in n is 1/2 in the first equation number 1, then this is going to be the integral from 0 to infinity t to the minus half e to the minus t dt. Then we are going to let t be equal to x squared. Okay, so what this means is that x is equal to square root t. It's just the positive value of square root t, not plus or minus, because t is always a positive number from the limits here. Then from here, dx is going to be dt over 2 times. Okay, maybe let me just write it like this. Is going to be t to the minus 1/2 dt all over 2. Okay, now t to the minus half dt we have there. That means t to the minus half is going to be 2 times dx. In terms of the limits when when t is 0, x is 0, and t is infinity, t is going to be infinity as well. So this function is now going to be 2 times the 2 is from here, the integral from 0 to infinity, and this is now going to be e to the minus x squared dx. Okay. Now, since x is a dummy variable, we can rewrite this in terms of another dummy variable y. Then if we multiply these two, then the gamma of 1/2 squared is going to be this times this. So let me just write them out here. 0 to infinity minus x squared dx, and then 2 times integral from 0 to infinity minus y squared dy. Then this we can actually write as a double integral from 0 to infinity, both in x and y. So dx dy. And then this we're going to write in polar coordinates. Before we do that, the region defined by those limits is just the first quadrant here. It's just the first quadrant. So if we write this in polar, then we know the limits in polar. So this is going to be 4 times the integral. R is going to go from 0 to infinity, and theta is going to go from 0 to pi on 2. This is going to be e to the minus r squared. Then this is going to transform to r dr d theta, where this r here is the Jacobian of the transformation from xy to r theta. Then this we can separate. So there's going to be the integral with respect to theta, and then there's going to be this integral with respect to r. The integral with respect to theta is straightforward. It's just going to be theta from 0 to pi on 2. And then this integral here, we're going to have to do using u substitution. Right, so in the second integral, we can evaluate that one using u substitution. So if we let u be equal to r squared, then du is going to be 2r dr. We have got r dr here, so r dr is going to be du over 2. The limits are going to remain the same, because when r is 0, u is going to be 0. When r is infinity, u is going to be infinity. So it's going to be negative half here. It is actually positive half from here, from the r dr. And then there's going to be e to the minus u du. Okay, now this integral here we've evaluated at least twice now, and we've seen that it's equal to 1. First we saw it in property number 1 here, and no, this is property number 3. So where we were already using the fact that we had done it here in detail, so we know that is equal to 1. So that means this is just 4 times pi over 2 times half, so it's just going to be equal to pi. So that's the gamma function of 1/2 squared. So this is telling us that then the gamma function of half is going to be the plus or minus square root of pi. Now let's just look at this integral here to see whether this thing can be minus. If we look at this integral here, so this is the integral of e to the minus x squared from 0 to infinity. E, we know, is always a positive function. So if you're integrating e from 0 to infinity, you are always going to get a positive value. So for that reason, we are going to have to discard the negative case here. So it's just going to be the positive case, and so this completes our proof. Right, in the next video we're going to look at how the gamma function can be used to evaluate some integrals that cannot be evaluated using your elementary methods like integration by parts, trigonometric substitution, etc. All right.